Okay, so this is lecture 7 of our class. Today we're going to finish the discussion about the testing part of DESeq. So how does it define a differential expression? In the last class on Thursday, we gave you the model. So specifically, the model is based on a two-layer hierarchical model for RNA-seq counts. So as a recap, here we use I to denote gene and J to denote sample. For every gene, every sample, we have a count, which we called Kij. And we consider that there are two layers in the data generation. The first layer is for the generation of a true count, not subject to measurement errors. So this is called Rij for true count, or you can think of this as a real count. And this follows a negative binomial distribution with a mean for gene I and for condition that sample J is in. So here the condition for sample J is either 0 or 1, means control or treatment. So we're assuming that gene I has one mean under the control condition and another mean under the treatment condition. And this is a dispersion parameter in negative binomial, which also only depends on gene I and the condition. So given this real count Ij, we multiply it with a sample J specific scaling factor or size factor Sj. And this multiplied product is what we consider as the mean of a Poisson distribution. And we're using this Poisson to introduce additional variation in the generation of the count we observed. So these are just the assumptions the model made for the data generation. And in almost every differentially expressed gene method, if it's based on a probabilistic model, you will always need to assume some distribution for the data. A lot of times, these distributions need to be justified before you assume them. But sometimes you will see that some methods assume them without justifying, okay, why is Poisson or negative binomial is reasonable. So I would say that in an ideal scenario, we need to justify. For example, we hope that we can have some data for us to verify, yes, the measurement is indeed Poisson-like. So something like that. So I just want to raise the attention that in the future, if you are a method developer yourself, you need to be very careful about whether the probabilistic model assumption is reasonable or not. And sometimes if you cannot verify it, you have to be honest that, okay, you assume this based on convention or convenience. Okay, so in the last lecture, we spent quite some time to talk about, yep.
So in a hierarchical model like this, where you don't actually see the RJ, how would you ever verify that Poisson is an appropriate distribution conditioned on RJ?
That's a very good point. So I would say for the Poisson step, you can verify it using spiking data. So in spiking data, in a biological sample, you insert RNA molecules with a known concentration, and that can be considered as Rij. So then the only measurement randomness is from sequencing, which is supposed to be captured by Poisson. And then the negative binomial is something, as you said, you cannot verify it because it's the biological variation. So I would say for that part, usually you just have to assume it. Yeah.
Cool, thank you.
Thank you. Yeah, so given this hierarchical model, then the biological question, whether this gene I is differentially expressed between two conditions, is translated to a hypothesis testing problem, whether Qi0 equals Qi1. And to answer this question, or to address or to provide an answer to do this hypothesis testing, we need to be able to first estimate the parameters in this model. And in this model, the key parameters include Qi1, Qi0, nu I1, nu I0, and also Sj. So in other words, for every gene I, we have 4 parameters for this MB in condition 0 and condition 1. We also need a sample-specific size factor for Sj. So these are the estimation procedure this paper DESeq uses. So I'm going to skip those because we spent time to talk about this last time. So now let's just assume that we have the parameter estimates. So now we have the parameter estimates. I will call them Qi0 hat, Qi1 hat, which are the estimates for the negative binomial means. And we also have those refined estimates for the dispersion. I'll call the new I0 hat star to be consistent with our previous notation, new I1 hat star. So 4 parameters per gene. And Sj is already accounted for, so let's just ignore that. Then the question is, how do we do the hypothesis test? So to tackle the test, here is the testing procedure proposed by the author. Let me present that first, and we'll discuss that. So the authors define Ki0 as the sum of the counts of gene I across samples in condition 0. They take the total for condition 0. And they also define the total for condition 1. J such that rho j equals 1, Kij. So they define those two things. And they argue that under the null hypothesis, they would have negative binomial, the 2 negative binomials. So they're using a property for, so I'm going to put that way. They are using a property of the summation property for negative binomial. So what they are saying is that they are assuming this thing. So they are assuming, okay, Ki0 is following a negative binomial itself as the summation of Kij's. So each Kij, put it here, each Kij, they are assuming that it's following a negative so it's like there's slight different thing. Okay, so they're assuming that each Kij, let's say that it's divided by the Sj. So it's assuming that this thing is following a negative binomial with a mean. And then, because for different j's, they share the same mean, which we call Qi0. So then they can take the summation and say that it's still a negative binomial, but the mean needs to be take a sum over it. So in other words, so let me just write it in a pretty abstract way. So they are assuming that the Ki0 itself follows a negative binomial, and Ki1 as the sum also follows a negative binomial. So I'm skipping the parameters for these 2 negative binomials just for simplicity. And they are assuming that if the null hypothesis is true, so under the null hypothesis that Qi0 equals Qi1. So if you think about this generative model, what it necessarily means is that all these samples for gene I are coming from the same negative binomial right here. So they are going to evaluate the probability that, okay, given this now being true, what is the probability for us to observe Ki0 equals the number we observe and Ki1 equals to the number we observe. So they're just going to calculate the probability for that. So here is what they define as the p-value. Let me give you that p-value first and let's revisit it. So given, suppose that our observed value, okay? So let's say our observed value is lowercase Ki0. This is what we observe in our data for these 2 numbers, Ki1. So they try to say that the p-value is computed as, is defined as this. Let me put it that way. So it's under the calculation that we have two numbers, A and B, okay? For those two numbers need to satisfy two conditions. The first condition is that A plus B must be equal to KI0 plus KI1, equal to the sum of those two numbers we observe. And furthermore, they require that the probability of numbers A and B is less or equal than the probability of numbers KI0 and KI1. What does that probability mean? I'm going to define it here. So they define the probability A and B as equal to the product of the probability that this KI0, which they assume to follow negative binomial, equals A times the probability which they assume to follow another negative binomial equals B. Okay, this is what they assume to be calculated. So it's going to be calculated from the two negative binomial. Maybe I'll call this 1 and 2. So based on distribution 1, and this is going to be based on distribution 2. And these two things are going to rely on the previous parameter estimates they derive. So based on these numbers, they're trying to do that. So based on and then they are going to, for these numbers A and B, they are going to compute their probability like this, and then they take the sum for all these A, B combinations. That's the numerator. And for the denominator, they define it to be all the A and B's such that A plus B equals to KI0 plus KI1. And they also do the summation. This is what they calculated or defined as the p-value. So do you see what is missing here, or what do you think as a problem here? So I can tell you that whenever I saw this p-value, I was very confused myself. I don't know why this is a valid way of defining the p-value. So that's why I'm presenting this to you guys for your examination and judgment. So I can see there are several questions I have about this, and you can add your points later. So the first question I have is, where did the null hypothesis get into play in this calculation? Where did we use this null hypothesis? I think it's strange that when we calculate this probability, we are using the condition 0 and condition 1 separately. And we didn't actually use this assumption that they share the same mean in this calculation. That's my first question. So where is this null hypothesis in the p-value definition? And the second question I have is that this p-value definition is essentially assuming that KI0 plus KI1 is equal to a constant. That's why when we consider possibilities, we're considering other integers A and B so that their sum is equal to this observed sum. But why is this reasonable? Why would we assume that gene I's total count in our samples is a constant? I don't see why. So I would say these two are the primary questions I have here. So I don't know whether you think about this, but I guess this is probably a very important reason why DESeq 2 has changed so much from DESeq. Although many people are still citing DESeq for the use of the DESeq software. So that's why this paper citation is super high. If you check Google Scholar, I think it's more than 10,000. But the testing approach is what I have a lot of question about. So to me, this is not a really valid way of doing statistical test. So probably it's worthwhile for me to review what are the essential components of a statistical test, just as a review of the basics of 100B, if you have taken that class or other classes. So after that, you can come back to this question again. So review of hypothesis testing. And also for your information, on last Friday, I and my PhD students gave a lecture or workshop to some biology background students about some basics of statistics, including hypothesis testing. So I'm going to share that YouTube link at the bottom of this lecture recording. So you can check that out yourself if you're interested in watching those basics. So in the review hypothesis testing, we need those 4 components. So the first thing we need is that we need the null hypothesis and an alternative hypothesis. We need them to be specified. And they are about some parameters. There are some conditions about the parameters. The null hypothesis is usually an equation about saying, okay, the parameters are equal to something, or 2 parameters are equal, like in our case, the means under the control and the treatment are equal. That's null hypothesis, it's an equation. Alternative is usually the violation of the null hypothesis, or it can be one-sided in some cases. So this first thing we need to specify is the null hypothesis and alternative hypothesis. And the second thing we need is we need a test statistic. Okay, and this is a summary of our data. So it summarizes data as a number. So for example, the T statistic, that's a summary. And we need to realize that this test statistic is random. The randomness comes from the repeated sampling we assume in our mind, right? We are assuming our data is only one of the many infinite number of possible samples, and we only observe one sample. That's our data. So that's why this test statistic is random, and we have a realization. The realization is on our data, on our particular data set. That's the second thing. And the third thing we need is to derive the distribution. Let me call this test statistic T. We need to know the distribution of this test statistic T under the null hypothesis. That is, assuming the null is true, what would be the distribution of the test statistic? And this distribution is across those infinite number of possible samples. So we're assuming that we can have many possible values of this T if the null hypothesis is true. Then finally, we want to compare, we want to place the realization of this test statistic, the number we compute on our data, onto this distribution. And we will realize, okay, how extreme is this number we observe compared to the distribution? So intuitively, the more extreme, which means that this realization lies in one of the 2 tails in the distribution, the more likely we are going to reject the null hypothesis. That's the intuition, because we think if the null is true, we know the distribution should be like this. For example, a T distribution for T-test, then it is very unlikely for us to observe a value as our realization. Then we want to reject the null. So the fourth concept is we define as the p-value. Okay, the p-value is what we define as the probability that we reject the null hypothesis at our realization, which we call lowercase t. That's how the realization of capital T on our data, or more extreme values. So here the more extreme is depending on how the alternative is specified. For example, in the T-test, if the H1 alternative is two-sided, that is the two means are not equal, then more extreme means extremely negative t-statistic or extremely positive t-statistic. We consider two sides. If the alternative is greater than, then we only consider the very positive values to be more extreme. So that depends on alternative. And we will reject that given the null hypothesis being true. So in other words, the p-value, you can consider it to be a conversion of the realization to a number between 0 and 1. So for given the distribution of t under the null hypothesis, every realization can be converted to a p-value. So that means p-value itself is data dependent. It depends on your actual data, while the distribution is not depending on your actual data. This is hypothetical. It's just depending on the distribution you assume that the test statistic will follow under the null hypothesis. Okay, so once you convert a realization to a p-value, finally, you will make a decision. That is, you reject the null or not based on a significance level. So finally, you will make a binary decision based on alpha, which needs to be pre-specified. And this is usually set to 5% for most people. But I would say the 5% is not something as a ritual. You can change this. It's just that how small do you believe to be a small enough probability? Okay, so then the decision is based on, you compare the p-value based on the relative order of the p-value and the alpha. If p-value is less or equal than alpha, you reject the null hypothesis. Otherwise, you do not reject null hypothesis. So ultimately, your decision will be a binary. That's how we call a gene as DE or not. So these are the 5 steps for doing a hypothesis testing. But one thing I want to make sure that everyone is aware of is there is an equivalent way of doing hypothesis testing without using p-values. So alternatively, you can do 4 as not doing the p-value conversion, but you find the rejection region of t given alpha. That is, you pre-specify alpha and you find the rejection region of the test statistic given its distribution. So the idea is that you want that the t statistic to be in the rejection region when the null hypothesis is true. So you're going to use this distribution of t under the null to find this rejection region so that this probability is set equal to alpha. So use alpha to find the rejection region. And then finally, your decision is to compare the realization with the rejection region. So you would reject the null hypothesis if the realization is in the rejection region. So I would say this alternative way is actually easier to understand for beginners. That is, this alpha is what you call the type 1 error of the test that you can tolerate. So which means that the null is true, but you make rejection. So it's a wrong rejection. But we have to tolerate that because we always need to have some sacrifice for the type of error so we can make discoveries. Otherwise, if we think about let me give you one example. So if you think about the distribution of the test statistic value under the null or under the alternative, I call this t given h0, t given h1. Okay, so if we think about this randomness in our test statistic value, so you don't know which is true, h0, h1, but you know when h0 is true, the test statistic will follow this distribution. When the alternative is true, the test statistic will follow another distribution. Although they are distinct, but there's a large overlap in the middle. So that means that whenever you observe a realization right here, you need to sacrifice some type 1 and type 2 error, which means that it's possible the t comes from this distribution, but still you reject the null. In that case, that's a type 1 error. But if the t comes from this distribution, which means alternative is true, but you do not reject the null, that means you make a type 2 error. So whenever there's overlap, you can never make a perfect decision. There's always some sacrifice. So therefore, the type 1 error is given by what you can tolerate, called a significance level. So in other words, if this is a one-sided test, okay, let me put it here. So the H0 is mu equals 0. The alternative is mu equals 1. So in this case, what you do is that given the null hypothesis, your test statistic follows this distribution. You want to find the rejection region such that this probability is alpha. So in other words, given the alpha, you call this your rejection region. And then whenever you have a realization on your data set, you compare it with the rejection region. If it's in the region, you reject. Otherwise, you do not reject. So this is the alternative way. But you see, why we need a p-value is that this way is not so convenient to use, because you always need to start with an alpha, find the rejection region, and then reject. And on the other hand, if you think about p-value, when we convert the realization to a p-value, we didn't use alpha at all. We just do the conversion based on the null distribution and the realization. In other words, in this case, we are just saying here, given this realization, we look at this area, this purple area, and we call it p-value. And when we do this conversion, we do not use alpha at all. So we can do this conversion regardless of alpha first. And then given these p-values, a user can set alpha with their own choices. They can set alpha to 0.1. They can set alpha to 0.05. And then they can just compare the p-values with alpha to make decisions. So that gives users more flexibility with the choice of alpha. So I would say that's the reason why we introduced the concept of p-value. But I would say p-value is not a very easy to understand concept. So we must bear in mind that since p-value is a function of the realization, as long as we realize that our data is random, so the realization value can change, then the p-value would also change. So that's why we said p-value itself is random, and we talk about plotting histograms of p-value across simulations. So that's what you did in your first homework. Just try to use simulation to do repeated sampling. So then you can see how your data vary, how the realizations vary, and how the p-value vary. Okay, so after such a review, let's come back to this question. Then the reason I questioned this DESeq is that if we look at the 5 steps we list here for hypothesis testing, it is unclear to me what the test statistic is. It seems that the test statistic is considered to be the probability. This probability itself is used as a test statistic. Then what is the null distribution? It's not really assumed. Yeah, because here the question is that the null hypothesis didn't really get used in the calculation of the p-value. So that's why I couldn't really make sense of it. So yeah, so that's all I want to say. And you can actually check it yourself for the original, check the original paper if you're interested in figuring out why this makes sense. But to me, this is just something we shouldn't do for hypothesis testing. And we cannot just come up with a number and call it as a p-value. Yeah, so if you look at this ratio again, the difference is that in the numerator, we added a constraint. That is for those 2 integers, a and b, their probability defined by this formula must be less or equal than the probability we compute on the actual counts. But in the denominator, we don't have this constraint. But still, I do not see how this is related to the null distribution or null hypothesis at all. So in the second homework I already posted, the option or extra problem is regarding another paper, a more recent one, which is about finding another differential concept in the CRISPR analysis. So it's no longer gene expression, but it's about CRISPR editing or CRISPR screening, a very popular technology right now. So I would suggest that you also use the concept I introduced here to examine that paper and see what issues you find about its hypothesis testing. Yeah, so my take-home message is that hypothesis testing is so widely used in bioinformatics because biologists are so used to p-values. However, p-values are often misinterpreted, and also a lot of p-values are not real p-values. They are just numbers between 0 and 1. So the key take-home is that if the p-values are not valid p-values, in other words, under the null hypothesis, the p-values are not uniform between 0 and 1, then we need to be very cautious, and we cannot use the Benjamini-Hochberg procedure we introduced for FDR control. So FDR control can only be used for valid p-values. That's the message I want to convey. So if in the future that your research encounters some issues, which means that you don't have confidence about whether your p-values are valid or not, my suggestion is that do not call them as p-values. Just report the numbers you have. And I think that's more transparent and will not confuse the readers for possible like Benjamini-Hochberg or FDR, those concepts. Okay, so yeah, coming back to this review, one last thing I want to say is, after I presenting those two alternative ways of making decisions about hypothesis testing, now you can say that this probability, the probability of making a rejection, given your rejection region you set, okay, this probability, which is set equal to alpha, is not equal to p-value. So they are different things, because the p-value is depending on your realization, while this rejection region is not depending on your realization. It's just determined by alpha. Okay, so do we have any questions before we move on? That's the last thing I want to say about this part. Okay, so that's it. So we have concluded our discussion about differential gene expression analysis. And then in the future, for example, that CRISPR paper, you can use those concepts to check whether the hypothesis testing is reasonable or is properly used there. So now the next topic I want to introduce is what we call statistical learning. Statistical learning is a very broad concept, which is, I think, term is originated from machine learning. But what's the difference between the two, right? We are changing machine to statistical. And statistical learning, I would say, compared to machine learning, it accounts more about the uncertainty in the procedure. While machine learning, at least some machine learning algorithms are more focusing on the prediction part, whether you can predict your labels accurately, those kind of things. But the uncertainty in the procedure is less of a concern. But still, there's a large overlap between machine learning statistics nowadays. So please do not overinterpret the differences in the terms. So just as you see that, I want to say, whenever you see something called statistical, it means that we are considering uncertainty in our procedure. That's usually the case. So just as machine learning, statistical learning can also be classified as two types, which we call the supervised learning and unsupervised learning. And in this class, we will focus on the unsupervised learning more. Because that's more the case, that's more common in biomedical research. So the key difference between supervised learning and unsupervised learning is that for every data point, or we say the ith observation, we have xi and yi for supervised learning, while for unsupervised learning, we only have xi. So the notation usually means that xi is a p-dimensional vector. You can consider this to be p features, like for each observation, if it's a cell in the single cell data for your project, in the ith cell, let me write it. So in the ith cell, you can consider xi to be the gene expression vector. The gene expression vector of P, let's say 20,000 genes. This could be the xi, okay? And if it's a supervised learning, we can also have yi, and yi is usually one-dimensional, so I'm just going to call that in the real number, but it can be more specific. For example, the yi could be just integer, and integer varies from 1 to k. So I can call this as the cell type of cell I. So if I have k cell types, then it's one of them. So then in the supervised learning and unsupervised learning, the goal is different. For supervised learning, our goal is to predict yi from xi. So in other words, we are trying to supervised. We are trying to find a function f which has argument as p-dimensional vector, so maps from p-dimensional vector to one-dimensional scalar, such that we want the fxi to be close to our yi for many i's. So here, let's say I have n observations, I from 1 to n. The goal is to find this function such that I can predict yi well enough from my xi. That's the supervised learning problem. And depending on the nature of yi, we can further classify to be regression or classification. Okay, so regression is for the case where yi is continuous. The most famous case is what we call the linear model, linear regression. So that's the easiest type of regression. So in that case, in linear regression, we are basically assuming that fxi, and we know xi itself contains p elements. It's a p-dimensional vector. So we can write xi just as xi1 to xip. Okay, so when we are doing linear regression, we're basically assuming the function f is some linear function of xi with an intercept. So we can call that beta 0 plus xi1 times beta 1 plus 2 xip times beta p. So we can write it as a linear function. That's what we call linear regression. Then the question is how to find this f. Or we can also assume this to be a nonlinear function, which means that we can add some nonlinear transformation to each element in xi before we convert or add them up into a function for prediction. So in terms of the regression, you can think of the currently popular neural network as a very complicated f. So it's a way of representing f as a multi-layer nonlinear regression, nonlinear function. Okay, and the second type of supervised learning is what we call classification. And in that case, the yi is not continuous but categorical. So for example, we may have the yi to be binary 0, 1. We call that binary classification. Or if yi has more than 2 categories, we call that multi-class classification. So for the classification problem, there is also a large class of algorithms that has been developed in the statistics and machine learning communities. For example, you might have heard of the support vector machines that can be used for classification as well as for regression. And also random forests, which is also first developed for classification, but can also be used for regression. And now the deep learning or neural networks. So it's just, you see, the distinction between regression and classification is not so major because it's only about whether yi, you should predict the response to be continuous real numbers or just categorical labels. That's the major difference. And in many algorithms can satisfy both purposes. And also some regression are actually used for classification. For example, when you hear the name logistic regression, even though it has the name regression in the term, but logistic regression is used for classification purpose. So it can be used to predict either the response being binary or multi-class. So it's a very flexible method. So I'm actually going to defer this for your own reading. So if you're interested in the supervised learning, I will strongly recommend a book which is very easy to follow and has a lot of examples in R. It's called Introduction to Statistical Learning. And this book is a book is used for our undergraduate class. I think it's probably 101 or 102 here. One of the classes uses this book. So it has a lot of R code and real data examples to follow. So that's something I would strongly recommend. And you can find the PDF version freely available online. So the authors have generously made the PDF available. But of course, we are very encouraged to purchase it if you find the book good. Okay, so that's the supervised learning. The reason I do not talk so much about it is because it's ultimately a prediction problem, right? And it's very easy to assess how well the prediction is based on cross-validation. So cross-validation, let me briefly introduce it. It's the commonly used technique for assessing a model. That means you divide your data into, say, let me just introduce the 5-fold cross-validation, which is commonly used, which means that you divide your data into 5 equal sizes, okay? Each data contains 1/5 of your observations. And what you do is that each time you use 4/5 of your observation for training, okay? So which is to find a function f hat for this purpose. And then given this f hat, you will use the left out 1/5 for validation. That is, you apply this f hat to observations in this validation cohort. So you will have so-called yi hat equals f hat xi. For each observation in the validation cohort, you input it into f hat to obtain the predicted values yi hat. Then you compare yi hat against the real yi, the real responses in the validation cohort. So hopefully these two are close to each other for every I in the validation cohort. So you're going to summarize this into something called prediction loss. And the smaller the loss, the better. So the nice thing about cross-validation is that when you do the training, the validation cohort data are not used. So then you are not having the issue with called overfitting. That means you just made the f hat to go through your data point. If you use every data point for training and validation, right? Then you can always set yi hat to yi, and then you will have 0 loss. But that's not good because you may fit some noises you do not want to have for your data. So that's why to avoid that issue, we use separate data for training and validation. So this is a basic concept in the supervised learning field. So you can see that this validation is very intuitive and very easy to interpret. So that's why I'm going to defer you to for your own study if you're interested. And I believe probably you will learn this from another class offered in the bioinformatics program. Also, I'm going to post a YouTube link I actually made for a research paper, which we used classification as an algorithm for addressing the cancer driver gene prediction problem. So for that paper, I actually made a tutorial for what I did for the analysis. So it's a very step-by-step R tutorial. So I'm going to share that link under today's recording. So if you are interested, you can check that out for the classification problem. Okay, so now let's move on to unsupervised learning. And that will be the focus of our class. And for the unsupervised learning, we only have the p-dimensional feature vector xi for the ith data point. And we want to make some findings based on the xi's. So we are going to discuss unsupervised learning problems in two types. One is what we call clustering, which we will talk about today. The other is dimension reduction, which we will talk about next. Both are very important problems in biomedical research. As I said, in biomedical research, often we do not have good labels YI. For example, in single cell data, although I can say, okay, the YIs are cell types, but still in many cases, we do not know the cell types that well. So that's why we are doing single cell RNA sequencing. We are hoping that we can discover rare cell types or new cell types from our data. So in other words, the XIs are the data we collected. For every cell I, we measure P gene expression levels using the single cell RNA-seq. And the YIs are not readily available, right? So then we only have the XIs. And how do we ask this question? How do we answer this question? That is, given we have N cells, can we divide those cells into clusters based on their XIs? Then that's the clustering problem. And we'll start from there. Okay, so for clustering problem, the data, we call them X1 to Xn. So you can think of them as the N cells you measure, and each cell has P genes. The first and most popular algorithm for clustering is called k-means clustering. So we're going to start from there. So even though it's a very classic algorithm, it's still very popular and very widely used nowadays. So when is k-means clustering reason or applicable? It is when you think, okay, for 2 points, I think a Euclidean distance is a reasonable distance metric for 2 data points. So it's depending on this so-called Euclidean distance metric. And this is the distance we actually use in our real lives. So if you think that in our real life, we have a 3-dimensional space, right? That's our world. And if you want to measure 2 points, the distance between 2 points, what you do is that you take the difference between 2 points in every dimension, and you square that distance in every dimension, take the sum of the square distances, and then you take the square root. That's the Euclidean distance. So here, let me write this as the distance between xi and xj is defined as the square root of the summation. Maybe I'll just write that as, or xi and xi prime. Okay, that's better. J from 1 to p, I take xi j minus xi prime j. I take the difference for the 2 data points in the jth dimension. I square the distance, I take the sum, and then I take the square root. That's the definition of the Euclidean distance. And in some cases, people call this the L2 norm. That's another way of saying the same thing. Okay, so k-means, what it means is that we want to find k clusters. So the number of clusters is set to be equal to k. This is something you need to pre-specify. And then what we want is that we want to find k centers so that
we will assign each of the n data points to its closest center to minimize the within cluster square distances. That's what we mean. So the goal is to find k centers, and we'll call them as M1 to Mk. And the k centers are also p-dimensional vectors in the same p-dimensional space as my data points, so that to minimize this thing, what I call is the summation and summation, double summation. So first of all, for every data point I will have its membership, okay? So the membership of xi is one of the k's. It goes from 1 to k. So what it means is that I assign the ith data point to its closest center. If it's closest to the first center, then ci equals 1. If it's closest to the kth center, then ci equals k. So it depends on which center point I is closest to. So what I do is that for all the points whose ci equals k, equals to lowercase k, I take the square distance between these xi and the center mk square. So I call this the within cluster sum of squares. And then I take the summation for k goes from 1 to big K. So I take the sum for all my clusters. So therefore, you see, in the k-means clustering algorithm, we actually require every point to be assigned to only one cluster. So these big K clusters are non-overlapping and they're exclusive. And together they make up they're composed of all the n data points. So therefore, you see, every data point only enters the summation for once. It's either in cluster 1 or cluster 2 or cluster capital K. So our goal is to find nk to minimize this. Okay, so then it's a minimization or optimization problem. Our goal is to find the cluster centers. Then what do we do? So this is something in your homework. And I'm also going to introduce the algorithm, but I'll leave the justification for the formal justification for the algorithm to yourselves for the homework problem. But today I'm going to give you the intuition of the algorithm. So the algorithm is what we call iterative, which means that we iterate between two steps. So what we do is we start with a random cluster assignment. That means we randomly assign the endpoints to k clusters. So I call that with random cluster assignments. I call them as C10 to Cn0. So the superscript 0 means that it's the initialization. Okay, then in step 1, so I will say at the, okay, let me use the name rth iteration. Okay, here the R is 1, 2, and so on until convergence. So in the first step, I will use the existing assignment to find the cluster centers. Okay, so update cluster centers. Here the centers means is actually means. So that is, I will call this as MKR. So this stands for the rth iteration. So what I want to do is that I want to find the center given the assignment, right? Seeing this objective function to minimize. Given the assignment being fixed, I want to find the center. So that is within each cluster lowercase k, I want to find the center mk to minimize this. So this should be defined as the minimizer. We write as argmin of possible p-dimensional vectors that can minimize xi. Oh, sorry, I think I missed one thing. This is something I need to correct in the notes. This is a bad notation, sorry. So this should be written as this, not square, because it's two vectors. Okay, so I'm going to clarify this. So this norm, I can specify as here. So this can be written as this double vertical lines. It means the L2 norm. So xi minus xj, xi prime. So this is the notation for this Euclidean distance. So in other words, you see that if I expand this, it's actually equal to k from 1 to capital K. And this is I such that Ci equals K. And then this term can be further written as J from 1 to P, okay? And I would have Xij minus Mkj squared. So in other words, this L2 norm or Euclidean distance square can be written as this. Because of the square, we get rid of the square root. Okay, so here we want to find the argmin of mk such that find the argmin of this summation j from 1 to p xij minus mkj squared. Okay, we want to find the minimizer of this term. And you can see that this is the quadratic problem, right? How do we find the minimizer to minimize the quadratic? We can take the differentiation for each mkj and set that derivative to 0. So we can show that this will give me mkrj, the jth coordinate of mk is just equal to the average here. So, oh, sorry, I forgot this thing. I such that Ci equals K for the data points here. So this will just be equal to the average. I can call that a name. Probably I can give that a notation. I call that NKR minus 1. From the previous iteration, the number of data points in cluster K, summation, and sorry, CIR minus 1. So that is the ith data points such that its assignment in the previous iteration is equal to K, Xij. So the average of the data points in the cluster K from the previous iteration. So given the assignment, I update the centers just as the cluster means for each cluster. That's the first step. And you can see that this step is doing a minimization given the assignment. Okay, and then the step 2 is that given the new centers, we update the assignment. So we'll update cluster assignments. And what we do is that we assign the ith data point to its closest center. So here, the center Ci in the rth iteration will be based on these M1R to MKR. I'll find which of them is the minimum, right? So I can say that this is the argmin for the K, which can vary from 1 to capital K. And I compare the distance between xi, that's the ith data point, and each of the cluster center k from the previous step. So whenever the k makes this the minimum, I return that k, and I call that as the new cluster's assignment of my observation line. So then the second step is saying that given the centers being those, I update my assignment to minimize, to further decrease this objective. So in the homework, I want you to write out what I said. So why can each step in the iteration reduce this objective? So for the first step, I already said that to minimize this, you need to take the derivative to find the mkj, the jth component of mk. In this second step, given the cluster assignment, you can show that by assigning every point to its closest cluster center, I will not increase this objective. So to show that, you need to rewrite the double summation in another way. So in this way, we are writing it based on first take the summation within each cluster, then you take the summation across clusters. So you need to rewrite this in an equivalent way as that you take the summation for data points I from 1 to n. And for each data point I, you take a difference with the center it's assigned to. So that you can show that by assigning it to the closest center, you can minimize this term given the centers. That's the thing I want you to write down for the homework. So it's more like a mathematical statement of what I said. And if you have questions, you can come to my office hours regarding how to write that formally. So you can see that for the iteration, every step is trying to decrease this objective or at least not to increase the objective. So this can ensure that after we run the iteration and we stop whenever the assignments no longer change. Okay, so stop when CIR equals CIR minus 1. If compared to the previous iteration, all the assignments are equal, right? Then we do not need to do the iteration furthermore. So we can show that because each step is doing decreasing in the objective function, we can ensure the k-means algorithm will always converge to a local minimum of the objective function. So k-means guarantees to converge to a local minimum of this objective function. So we write it again. And in this objective function, there are two things we need to search for. We can call this a function of two things. One is the centers, the other is the memberships. So the centers are the things we need to find. This is the assignment, and this is the center. Okay, from 1 to capital K. So we will find both of these things. And we hope that we can find the assignment and the centers to minimize this function. But as I said, this iteration can only guarantee that you converge to a local minimum of this function, but it may not be a global minimum of this function if this function has many local minimum. So what we mean by local minimum and global minimum, let me just give you one simple example. So let's just say that I have a function of fx. So if the function looks like this, okay, so we will say that this function has two local minimum. One is here, one is here. But this is the global minimum, while this is not. However, if your algorithm is like this k-means algorithm, and if you start from here and you go down, 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 because every step you will always go down. So you will not go up here. So you will be trapped at this local minimum and you will never find this global minimum. That's the issue we are talking about here. So to address this issue, the only way is to use multiple random initialization here. So that's why in the R function k-means, you can see that its default is to do 10 random initialization in the hope that for at least one initial randomization, you can capture this global minimum. That's the hope. If the function is not too complicated, hopefully you can find the initial start that can lead you to the global minimum. But it's not guaranteed as always. So what we do is that once for every initialization, we will converge, right? And we compare the objective function at its converged point. And then let's say we have 10 random initialization, we can calculate 10 values of the objective function after convergence. And we will pick the value that's the minimum across the 10 values. And then for the minimum value, we find its corresponding assignment and centers. That will be the result we report.
Dr. Lee?
Yeah.
Is it possible to say, look at the values of the objective functions across, all 10 of these and decide, okay, they're not clustering around some small value, so we need to do, say, another 10 or 20 or 30 evaluations?
So what do you mean by what I didn't really get your point.
I guess so. Let's say you do the k-means clustering 10 times, right?
Yep.
And so you'll have 10 minima for the objective function, right?
Yeah.
Presumably, if all 10 are the same, you're confident that you've got a good probably the global minimum, right? If all 10 are, say, very, very different from each other, would you then do more? Is there any kind of evaluate? Yeah.
That makes sense. Yeah, I agree. I think that's a very good intuition, because if all the 10 values are different, you will worry that probably the f function is too complex, that it has too many local minimum, so that you want to explore more to see, at least you want this global minimum to be captured by multiple initialization, then you feel confident, right? That's what you mean.
Yeah, I think so. Yeah, thank you.
Yeah, I think that's correct. That's exactly what we want. And also there's an algorithm you can check out. There's a Wikipedia page for that. It's called k-means plus. And k-means plus is a very popular algorithm for specifying the random initialization. So the intuition is that when you specify, so what it does is that it's not doing random cluster assignment for initialization. It's doing random k cluster centers for initialization. That's what it does. So what it tries to do is that it tries to specify k centers to be equally far away from each other, so that you can hopefully that given those k centers, when you do the initial assignment of every point to the closest center, hopefully you can make the k clusters far away from each other good enough, so that you're not less likely to be trapped in a local minimum. That's the hope. Yeah. So for example, a typical local minimum of k-means can be like this. Let me give you a bad example. So let's say if p equals 2, okay. Okay, and I call this as xi1, xi2. So you understand it's the 2 dimension. So if you have like a cloud here, okay, and if you have another cloud here, that's how your data look like. So you want to have this cloud one cluster, this is another cluster. But it's possible when your initialization is not very good, you may divide the data points in this way. So this part is called one cluster, and this is called another cluster. That's possible. So that's the thing you want to avoid. And this can be addressed if you specify the initial centers to be far away from each other. And you can sometimes avoid this issue. Okay, and another case where k-means do not work well. Okay, I can give you another example. So when k-means does not work, that's when the Euclidean distance is not a good metric. So I can give you an example for that. Still, let me talk about 2 dimensions for visualization. So this is what's called a Swiss roll problem. So if the data points are falling in a bigger ring and a small cloud in the center, in this case, the Euclidean distance is not a good metric, because what you want is that you want these points to be in one cluster and this to be another cluster. But clearly, in the range, the points are very far away from each other in Euclidean distance, right? So k-means will never find this pattern, will not divide the center into one cluster and this as another cluster. So how do we address that? So for this problem, we have something called spectral clustering. So which we're not going to introduce in this class because this spectral clustering requires some knowledge about matrix, eigenvalues, eigenvectors, those kind of things. We're not going to introduce that, but just for your information, spectral clustering can be used to address this type of problem. What you do is that you are going to transform your data not in the original 2 dimensions, but to a new space. And you hope that in the new space, these 2 clusters can be better separated. So I can give you one example about how data transformation can work. And that's actually the idea in support vector machine, if you know that method for supervised learning. So this is an approach called kernel methods or kernel transformation. So the intuition is that we want to project our data to a higher dimensional space. So for example, for p equals 2, if we can project the data to a 3-dimensional space in a way so that in the 3-dimensional space, maybe in the vertical mu axis, we can have the center dots lower while the ring higher. If we can project into that 3-dimensional space, then we can just set a cutoff on the 3rd dimension so we can separate the ring from the center. That would be an intuition for that kernel method. It's a way to project the low dimension into high dimension. And so Helen, okay, I see there's a question from the chat box. I just saw it. It's from Albert and Helen. So Albert says, why is k-means dependent on the Euclidean metric? Could you replace the Euclidean with a more appropriate metric? Exactly. Yeah, change the objective function. Definitely. You can change this object, this metric from Euclidean space, but then it's not k-means. The reason it's called k-means is because the centers are means for the first step, right? So if you look at this first step, if you change this distance to a different metric, then the minimizer may not be the mean anymore. So it will not be called k-means. So that's exactly the thing we want to talk next. So we can say that we can replace k-means by k-medians so that the centers are medians instead of means. So when is that case? Let's look. So the variance of k-means, k-medians. So in k-medians, what we change is that we change the L2 norm to L1 norm. So let me give you the motivation for that. So L1 norm in the one-dimensional case, okay, if each xi is one-dimensional, p equals 1, then there's no difference between the norms. So they are the same distance. But if it's p-dimensional, so the L1 norm, which we write as xi minus xi prime to data points, with the subscript I for L1. So if there's no subscript, it means L2 by default. That's the convention. So this is just the summation across dimensions from 1 to p, xij minus xi prime j. We take the absolute value. So that would be the L1 norm. And we can show that this is a fact which you can show, it's a very important fact we use here. So if you want to find the minimizer, or we can say the argmin, still let's use the notation mk, okay? In p-dimensional, I want to minimize this L1 norm. Sorry, I should say that I, ci equals k. Okay, I still need to keep that xi minus mk L1 norm sum and summation across the point xi. And if I expand it, it's based on the definition here. And ci equals k, okay? And I need j from 1 to p. It's the absolute value of xij minus mkj summation. That's the L1 norm. So I can show that if I want to find the MK coordinate by coordinate to minimize this, I need to have the is equal to this. So the MKJ, the J coordinate I need is actually the median of X1, okay, I'll just say Xij for the i's such that they are in the kth cluster. So I will take the points in the kth cluster and I will pick their jth coordinate. And of those jth coordinates, I pick the median. And I can show that that median would minimize this summation for the jth dimension. So this is a very important fact for L1 norm or sum of absolute values. And then you can see that here why distance matters. For a different distance, then the center that minimizes the objective function can be defined in different ways. Okay, so here it is. If you want to use the L1 norm, then the k-means become k-medians. So the centers will be medians instead of means. An advantage of that is, median is less sensitive or more robust to outliers, while the mean is not. So if that's something you desire, you would use k-medians instead of k-means. But I would say to find whether k-means is reasonable, usually we will plot our data first, and that requires dimension reduction. Once we learn how to project p dimensions to 2 dimensions, then you can see that's a way to examine for outliers. Then possibly you want to remove those outliers from your data before you do cluster. Okay, so let's stop here for today. And I'm going to post the recording and the relevant links to our YouTube so you can check it out there.